able to get to them and try to get through all of them towards the end of this presentation. So thanks again for joining us, and I'll let Jason take it away.
Thanks, Jess. That sounds good. Good to see everyone. I see a lot of familiar names, so I appreciate you guys jumping on and joining us today. As Jessica said, today's topic is improving digester performance through the use of recuperative thickening. For those I haven't met or may be new to, let's say, the Fluence webinar Tech Talk series, I'm Jason Bowman, so I oversee our industrial wastewater and biogas operations for North America, biogas being the key word for this presentation. So what we'll do today, we'll go through about 30 or 35 minutes worth of, let's say, 20,000 or 30,000 foot overview of what recuperative thickening is. And if you guys have any questions or comments or anything, as Jessica said, throw them in the chat box. Of course, you guys can always feel free to reach out to me by email or give me a call. So let's get going. All right, so let's get started. For today's agenda, we will focus on 4 main categories. We'll start with a brief introduction on how digesters are typically classified, and then we'll discuss common reasons why these digesters fail. We'll then discuss and focus on how recuperative thickening works and how it can be applied to both new builds and digester retrofits before discussing the most applicable market segments that recuperative thickening is typically applied to. So let's get started. First and foremost, let's briefly discuss how digesters are classified. For those who have followed our previous webinars and tech talks, you've probably heard me discuss how many different digester designs are available commercially. The photos in this slide do a pretty good job of showing a wide range of Fluence's own digester configurations, but there are other options beyond this. The main reason for this is that not all wastes or wastewaters are created the same. Generally speaking, you'll find 2 main classes of digesters. First is the more classical, let's say, complete mixed digester. So these are generally utilized to manage things like waste slurries that are high in organics and volatile solids. So these units have been in operation for many, many decades. They date back a long time and are applied to a variety of project models, which we'll get into momentarily. But these are generally applied to municipal biosolids, food and beverage sludges, meat, agricultural processing operations, etc. The second class of digesters is what we call high rate or rapid digesters. So these digesters are typically utilized for waste streams that contain lower solids, but still have a relative, let's say, medium or high degree of dissolved organics. So these systems are relatively newer in principle, but have been applied for a few decades now. And these rapid digesters are typically granule-based biological systems. Beyond the physical classification, that is the difference between sludge digesters and rapid or high-rate digesters, I think it's also important to classify digester project models. So I generally refer to digester projects in one of 2 ways. First, we have exactly what the name implies. They are digesters for digestion. So these project models are geared more toward reducing sludge volumes or stabilizing sludges for less and or more manageable transport and land applications. So these systems are generally part of a larger energy-driven project where the goal is to maximize the biogas output. And for this reason, this is why you often find these types of digesters either in the municipal market or in a developer-driven market. That means companies will basically finance these projects to create an operation that produces excess energy. The second project model is when anaerobic systems are utilized for wastewater treatment. That is the core treatment for these facilities. So here, when we say wastewater treatment, what we're saying is these units are configured as the primary wastewater process And you'll find these units applied to industrial operations with medium to high flows and a high degree or medium to high degree of dissolved organics, but typically lower solids. So you're not dealing with the big thick sludges or byproducts. When these industries are required to meet specific POTW discharge limits, that's where you typically see this type of anaerobic process used. In other words, these systems are typically applied when conventional aerobic systems, that is, aerobic wastewater systems, can really no longer be considered because there are issues with excess energy or excess sludge production or having excess hydraulic retention time required. So now that we have a more, let's say, defined sense of how digesters can be classified, we can focus on the most common reasons why these digester systems may fail. To be clear, I believe that you can make any technology work in the right setting, just as you can make any technology fail if it's applied incorrectly. The best available technology could fail miserably if we fail to understand its market and design limitations. So similar to how I discussed the two categories of digester classification, I typically also refer to digester failures in terms of two potential categories. The first being we have design failure. So this is basically the inability to identify problems or predict problems or our inability to see the full project roadmap in advance. The most common design failures revolve around poor project characterization or the inability to clearly define project objectives. In the developer-driven market, we also see an emphasis placed on maximizing biogas for energy and or profit. And this is typically at the risk of ignoring all the ancillary systems required to actually provide the most reliable system that meets local regulatory standards. We've run into a lot of projects where developer-driven projects tend to ignore what happens after the digester in certain situations or how to manage the biogas. So to finish outlining the most common design failures, we have organic only focus. So basically thinking only of the part of the waste that generates biogas and ignoring the other contaminant loads like the nitrogen or the ionic activity. So when we talk about ionic activity, that is, we're basically ignoring the potential impact of like dissolved salts, solids, and molecules that will essentially combine and or precipitate under reaction inside of these reactors. Beyond that, we also have the organic loading rate, that is the OLR, and the hydraulic retention time, that is the HRT. One common assumption is that lower organic loading rates or longer hydraulic retention times are often better. But in fact, it can actually be harder to operate an underloaded system, that is something with too low of an organic load, versus an overloaded system. Note here that we are keeping the SRT separate. In some digester configurations, there is actually no ability to control the SRT, so that's the solids retention time. So we're going to speak more on this later because this is a very important facet of recuperative thickening. The second form of failure is operational failure. So when digesters are overfed, it's possible to create an excess of volatile fatty acids, that is VFAs, which can suppress biomethane output or create pH issues, or it can actually create too much gas that can actually displace valuable biomass from the system. Just like any biological system, whether it's anaerobic, anoxic, or aerobic, having the proper pH, alkalinity buffer, and nutrients available is paramount to ensuring a healthy system. So to round out the rest of the most common operational failures, we have precipitation. Basically, this is what can occur or can cause poor mixing, can cause blockages. Basically, molecules under certain pH, under certain alkalinity conditions, under certain temperature conditions can actually start to combine and perform precipitants. This generally occurs when the ionic activity is intrinsically high and or different wastes are being combined together. Temperature is also a very critical part of successful digester performance, obviously. almost all digesters are going to require at least mesophilic temperature conditions. So a lot of projects actually fail to account for proper heating or fail to account for the fact that you have to utilize a portion of the biogas being produced to actually provide enough heat to the digester to make sure that it's always in a mesophilic range and to keep your removal efficiencies at a high level. So obviously this can therefore take away from the potential energy generation of the system, of the total system. So for this reason, you'll typically find systems with both incoming and recovery heat exchanger units that can try to recover as much heat as possible. Beyond that, perhaps the biggest operational failure that we have seen is actually treating the digestate, which I mentioned a minute ago. Digestate often goes overlooked, or people assume, operators assume, designers assume that it can be managed by hauling or through land application. You've probably seen or heard some of the other tech talks that we've put out. The land application side of things or the hauling application side of things is not always the case. It's either the economics don't work out or the physical regulatory requirements don't allow such. So just keep in mind as we're talking about these systems, a gallon of digestate can be the equivalent of up to 50 gallons of municipal waste. So proper design and operation of digestate treatment is critical to keeping these projects on track. So let's pause here for a moment because this is a really important slide that kind of dictates the rest of the presentation. While it's a very basic slide, the items highlighted will become more and more important when we discuss why and how recuperative thickening can ensure that these 7 items are more manageable and not the reason that our digester failed. So let's look at item number 1, lack of biomass control. So traditional systems, that is the classic CSTR style complete mix reactors, are basically a in equals out operation. That is, you have a tank that's full of waste or wastewater. For every 1 gallon that you put in, 1 gallon leaves the system. Other than the mixing and the chemical systems, there's virtually no way to actively manage the biomass concentration in these reactors. So traditional systems rely on the proper feed and chemistry up front to ensure sufficient biomass develops. Item number 2, loading stability. So traditional systems have been designed around either a reduction in sludge or the ability to generate massive amounts of biogas. So in either case, it's possible for operators to try to overload the system, assuming that they can either reduce more sludge or assuming that they can produce more biogas. Also, conversely, though, sometimes incoming feed is not available, or maybe a factory or a feedstock is off for the holidays, as an example, and isn't physically producing waste. So you as an operator, as an operation, are not physically getting waste into your digester system. Either way, periodic underloading or periodic overloading can shift the balance of the biomass and potentially create a snowball impact for operators. They start chasing their tails to try to manage not having enough food or having too much food. Failure number 3, mixing. So most classic digesters rely on mechanical mixing, whether these mixers are vertically mounted inside of the tanks or externally side mounted. There's some form of mechanical mixing. Uniform mixing in these systems is critical to ensuring stable output as well as infrastructure health. So settled solids in these situations can create corrosive conditions, and in worst case scenarios, it can actually decrease the overall operational volume, thereby decreasing the HRT if the mixing is so poor that so many solids are settling inside of these reactors. So common failure number 4, VFAs. I briefly mentioned this, so volatile fatty acids. Those that have operated digesters likely understand why VFAs are a good thing, but can also be a bad thing. So VFAs are a critical part of the 4 anaerobic metabolic reactions. But if these are left unchecked or left to increase uncontrollably, VFAs can actually hinder performance. They can actually drive the pH down, and they can actually stop biogas production if it gets bad enough. So traditional digester systems generally adapt for this by trying to understand what waste is being added, what your feedstock is, and continuously monitoring the pH and the alkalinity as it relates to the incoming organic load. But still, at the end of the day, for these classical systems, there's really few external control mechanisms to help balance these systems, beyond these initial operational inputs, your feedstock, your pH, and your alkalinity. So point number 5, that is toxicity. So this can cover multiple areas, but for the sake of this presentation here, I am specifically referring to ammonia toxicity and sulfur toxicity, and that is H2S in the biogas as well. Digesters typically have a toxicity limit for both ammonia and H2S, generally in the few thousand ppm or milligram per liter range. In traditional systems, again, there are very few operational control measures to allow a system to rebound or adjust in real time when toxicity limits are reached. Failure number 6, that is precipitation. Again, I briefly mentioned it, but this can be one of the hardest things to predict in these systems, specifically for systems who are reliant on taking mixed food waste or various sludges and byproducts from different industries, whether it be manure, agriculture, food and beverage, etc. So things like calcium scaling, calcium phosphates, and even struvite are common precipitants when you start combining various waste sources alongside of normal system pH and alkalinity adjustment, the normal chemicals that go into the process, and the wrong combinations that can create these precipitants that will basically fall out within the reactor, plug pipes, settle on equipment, settle on the tank floor, etc. So number 7, SRT control. This is the last thing I'd like to highlight. Almost all biological wastewater processes have some form of SRT control. The traditional digesters are the exception. Most biological processes will separate bacterial solids from excess solids in the liquid fraction, and a portion of this is typically returned to help stabilize biomass concentrations in these operations. However, traditional digesters lack this control. Going back to that in equals out equation, 1 gallon in is 1 gallon out. There's really no recirculation going on in these systems. So this is also why traditional digesters require excessive storage time. All right, now that we've covered the various classifications and common reasons for failure, without further ado, we arrive at the point of this presentation that everyone is here for, and that is recuperative thickening. So let's first discuss what this process entails before identifying its benefits and applications. Recuperative thickening is a process that aims to collect treated digestate, that is what's coming out of these digesters, and partially separate that digestate into its liquid and solids fractions. A typical recuperative thickening unit will generate concentrations of digestate up to maybe 8% solids by concentration. So this is managed through both chemical and physical mechanisms. A portion of this thickened biomass is then recirculated, much like you would find in a conventional activated sludge operation for wastewater treatment. The fraction that is recirculated can then be controlled to balance the biomass inventory in relation to the incoming loading and the incoming feedstocks, as well as the mixed liquor suspended solids needs or even the solids retentions needs. So we as Fluence utilize our own specialized DAF process to perform this liquid solid separation. This is really the heart of recuperative thickening for us. This specific unit is designed to manage digestates and is capable solids loadings up to 170 pounds per day per square foot, or for you metric people, roughly 35 kilograms per hour per square meter of effective DAF area. So for those of you that know DAF operations, know that these numbers are quite a bit higher than your normal DAF operation. Again, this unit is designed specifically for digestates. So the very first question that we're typically asked is, well, how do you control the saturation levels? That is, how do you keep from transferring oxygen into a stream that is being recirculated back to an anaerobic process? Well, the short answer is it's quite simple. The relative strength of the digestate is quite high compared to almost any other type of DAF operation that's separating solids and liquids. So compared to the digestate strength, compared to the volume of the air provided, oxygen is consumed very rapidly and almost always ensuring there's no dissolved oxygen remaining in the recirculation loop. So the second question we typically receive is methane an issue? Obviously, you have a digester, it's producing biogas. A very large percentage of that biogas is methane, CH4. The short answer is no. Methane is not transferred into or out of the DAF unit. We do not use biogas for saturation. We're using compressed atmospheric air. Again, that oxygen, that air is consumed very rapidly. So there's no need to have a need for explosion-proof room or have the DAF in a segregated area for that purpose, for that reason. So now that we know and understand the basics of recuperative thickening, how and where do we apply recuperative thickening? The largest market segments for us typically fall within the dairy and meat processing verticals. Really, any process with a high degree of carbohydrates, proteins, and lipids would be a good candidate. And these systems generally focus on wastes with both a high degree of organic content and volatile solids, meaning these systems are perfect for waste with COD values well in excess of 100 grams per liter or 100,000 milligram per liter. Through the biomass control, we can actually maintain whatever SRT is necessary. We typically like to see an excess of 20 to 25 days in our system designs. So this typically means that we're either going to be half the size of traditional digesters, or we can actually double the capacity of existing digesters. So what does the actual process look like? Well, here we have a nice process block flow diagram. I could show you a picture of a DAF system because that's really what it is, but there's just a very special control mechanism and control philosophy that's built into these systems. So if we look at the block flow diagram, essentially what you have here is a traditional digester with one important addition, and that is the biomass thickener. The biomass thickener here, again, our specific anaerobic DAF process receives all or maybe only a portion of the treated digestate, depending on the final project objectives and how much recirculation is needed. Once we receive the digestate, it's thickened in the same way that most DAF units already operate. So we can thicken our solids up to 6, 7, 8% in most cases, and then we recirculate that thickened biomass back to the digester. The added benefit of this biomass thickener is that it also offers an initial level of clarification. So it's kind of a 2-in-1 process, meaning the liquid fraction is typically or relatively clean compared to most digestate operations. So what this means at the end of the day is what goes out of the DAF, the clarified DAF effluent, has much less loading and much less solids that are going to, typically it's a downstream wastewater process. So we can actually reduce the loading and the burden to downstream processes with this type of process. All right, so what other benefits can we expect? So if we go all the way back to the common reasons, the 7 common reasons I noted for digester failures, we can start to manage each of these 7 failures more distinctly. So we already know that we can thicken the biomass and create a mechanism for controlling the mixed liquor volatile suspended solids inside of this reactor. If we go all the way back to slide 13, I think it was, if we go back to point 2, under our failure slide, we now have the ability to manage biomass, whether the incoming load is reduced or increased. The method of recirculation here with the thickened biomass is typically directly proportional to the incoming COD load. So the higher the COD loading, the higher the recirculation rate that we have in these systems. So very straightforward. This recirculation provides crucial mixing as well and helps to homogenize the slurry inside of the reactor. So we're getting a bit of additional mixing boost inside of these systems. By controlling the biomass recirculation, we can also provide a level of real-time adjustment during periods of increased or even decreased VFA activity. So as with activated sludge, as an example, this specific recirculation to this digester unit, this specific method ensures a healthy, stable, but also a diverse population of anaerobic bacteria are being returned. So this helps provide additional balance or buffer or stabilization to ensure that your acetogenesis and your acetogenesis steps are balanced and that your VFAs don't run rampant in one direction or another. Again, going back to the common methods of failure for ammonia toxicity, in these systems, we can actually do what we call ammonia dilution, where we often add in struvite recovery or struvite removal within the side stream of these systems, meaning that we can actually remove or recover ammonia. For those of you that know the struvite, it's a 1:1 to 1 molar equivalent magnesium ammonium phosphate. So we can actually help minimize the ammonia concentration and minimize precipitation in a lot of these reactors by having the side stream struvite recovery process. One very important note to all recuperative thickening systems, these are not typically applicable to manure and agricultural operations. That is because those type of operations typically have some very specific types of colloidal and lignin-based content in the systems, and it does create challenges for separating and thickening those type of slurries. Now, I apologize, this image is a bit tricky. It's a little busy here, but I wanted to share an actual process flow diagram outlining the various recuperative thickening steps. So if we go over here, we can clearly see our digester is kind of the central piece of the equation here of this process, of this operation. But on the backside, when we say recuperative thickening, this is really what we're talking about. We're talking about our specific anaerobic dissolved air flotation mechanism. It's typically polyelectrolyte only. Sometimes, depending on the exact feedstock, the exact waste that we're digesting, we may need to change the chemicals, but typically polyelectrolyte is all that is required. Sometimes ferric chloride is actually a good thing in these systems. They can help kind of maintain the H2S buildup within the reactor itself. But you can see here, we typically have a recovery pump. We have a series of heat exchangers, both in line up front and both in the recirculation process. Again, just trying to maximize the heat recovery. Biogas goes to a very specific biogas desulfurization process, again, by Fluence, and always with the safety flare. You need that on every project. The struvite and ammonia reduction system we have highlighted here, this is what we call, it's a defosphization unit. We call it our Fostrex, that's the Fluence name, or Fluence brand, I should say. But again, at the end of the day, this is primarily for magnesium ammonia phosphate reduction, i.e. struvite. So you can see typically from the dissolved air flotation process, we're returning the majority of the solids. Excess solids or clarified liquid we would send either to the wastewater plant, or we would send to further, let's say, solids handling, whether it's a screw press, belt press, what have you. There's a number of different ways that we can handle that. All right, now that we've covered the technical and application side of things, let's check out a few sample projects. Now, we as Fluence have been quite successful within the dairy space. I guess having our core operations, our core biogas center of excellence located in Europe, Italy specifically, has allowed us to have access to some of the most prominent regional and global dairy companies. So here we have a few systems highlighted within the dairy processing industry. As I mentioned earlier in the presentation, the dairy processing market is one of the best fits for this type of technology, given the waste profile and the historical challenges with classical digesters or classic CSTR digesters. So just looking at the photos, you can actually get a perspective of the size of these digesters. These are not huge systems that everyone expects. These are much more compact than your traditional CSTR systems. In some cases, 2 or 3 times less volume, less footprint. But perhaps one of the most critical features of the recuperative thickening process when applied within the dairy market specifically is the ability of this process to manage various waste sources. Waste sources in the past have been viewed with a bit of skepticism, whether they go to digesters or they go to feed or animal feed or land application and some crazy applications. But whether it's acid whey, salty whey, or even sweet whey, we can actually use recuperative thickening and apply this to balance both the bacterial side of things, but the solids requirements as well associated with treatment of this type of waste. So we've come to the end of the technical side of things, the application side of things specific to recuperative thickening. So this almost wraps up the presentation. I just wanted to say thank you once again. For those of you who may not know Fluence's global presence, we are quite a large company. We do have offices in 13 countries, covering projects in over 70 countries. And in addition to what we've covered here today, in addition to the waste to energy, the anaerobic digester systems, we do have divisions dedicated to the more complete water cycle, ranging from decentralized treatment to desalination, to municipal and industrial water use, and of course, our industrial wastewater operations. So with that, we come to the end of the presentation. I really appreciate everyone's time. I hope you were able to get something out of the presentation. Obviously, there's a lot more technical detail, technical information that we could go through, but for the purpose of trying to keep this to half hour to 45 minutes, we kind of hit the 30,000 foot overview. So with that, I think we'll open it up to questions. We'll hang around for a few minutes and see if there's any questions, try to answer any questions that you guys have. And if you think of anything in the future, you can see my contact information here. By all means, please feel free to give me an email, give me a call. I'll be happy to talk to you in more detail.
Great. Thanks, Jason. Appreciate it. We do have a few questions in the chat coming in. Are you able to see those, Jason, or would you like me to read them?
It looks like I'm going through them right now that I have backed out of the main screen here. So we have the chat side and we have the Q&A side. So I'll do Q&A first, and then I'll hit the chat, if that's all right. So let's see. All right, Martin, have you tried or experimented with centrifuges or probably hydrocyclones? No big deal. Just wondering as regards applicable to known thickening devices. I think the short answer is no. I mean, with the DAF process, most digesters, when you get into these situations, you really don't want to go more than 8% or 10% solids. So centrifuges are probably a bit overkill from that perspective. Hydrocyclones, that would be quite interesting, because I know there's a lot of work going on with, let's say, more conventional wastewater treatment systems, like aerobic systems, where you can kind of separate, like phosphorus organisms or POAs. You can separate lighter slurries from heavier slurries so that you can, let's say, increase the settling rate, or, send back the lighter stuff to the biological process and let it go through once more. So That would be interesting, and I'm not sure we could get the percent solids that we would likely require in some of these situations, but interesting question there. So let's see. Second question, Martin. Thanks for sharing, Jason, Fluence team. Now mostly mentoring university students. Yes, Martin, I did get all of your emails. I appreciate the support. So let's see. We'll jump over to the chats. All right. Let's see. I see Martin's first question was in the chat. So first question, is feedstock just entered at full value? Example given 20,000 COD to reactors or some sort of dilution to be utilized. In yes and no. So keep in mind, a lot of the slurries and sludges that we're getting in these situations are actually primary DAF sludges or biological sludges or byproducts from these operations. And when you get into, let's say, primary DAF sludges, they're taking a lot of the volatile solids and FOG from the primary waste stream. It's not uncommon to see 60,000, 70,000, 80,000 ppm COD equivalent in those sludges. When you get into byproducts, some of the wheys and some of like the raw product, if it's milk, cheese, certain meat proteins, it's not uncommon to see COD values even higher in the 100,000, 150,000 ppm range. So depends on what we're combining. These systems I would say we try to keep the total COD value somewhere between 100 and 150,000. Once you get above that, it can create an issue. Not necessarily from a digestion perspective, but more of the higher COD concentration, the more recirculation you need in a recuperative thickening process. So it just becomes kind of an energy balance, and the more recirculation you have, then you're kind of balancing the HRT and the SRT of the system again. So from Roberto, is ammonia removed thanks to the air used in the DAF? No. So when I mentioned ammonia and ammonia toxicity specifically in these systems, when you get into industrial operations, mixed food waste, primary DAF sludges, byproducts, and particularly on the waste side of things, acid waste, salty waste, things like that, you actually end up with a lot of magnesium, you end up with a lot of ammonia, TKN, and then you end up with a lot of phosphorus. So we, in a lot of cases, proactively try to, maximize the molar ratio of magnesium to ammonia to phosphate to phosphorus. And we actually not strip that out, we precipitate that out in a side stream as struvite. And so when I say ammonia toxicity and ammonia recovery, that's what I'm talking about. We're actually pulling the ammonia out of the side stream. So in addition to that recuperative thickening side stream, we can add in either like a magnesium oxide, magnesium hydroxide addition, so that we can help bind ammonia phosphorate to that magnesium to create struvite. And let's say you had 100 parts of magnesium, 100 parts of ammonia, and 100 parts of phosphorus. You could probably expect to see something like 50 or 60 parts of ammonia reduction. And so in some of these systems, when you're talking about 2,000 parts of ammonia or 800 parts of phosphorus, magnesium is often the limiting factor. So in some systems, we'll add magnesium hydroxide or magnesium oxide and purposefully precipitate in that side stream, remove that out of the process so that we're decreasing the amount of ammonia within the reactor itself. So next question, one important aspect to keep in mind with recuperative thickening is that the secondary wastewater treatment process received a large load of ammonia. You're typically pretty right there. The plant will need to make sure that the aeration system can handle that additional ammonia load. Absolutely. And it depends on what you're treating for sure. If we're not using a struvite removal process and proactively removing ammonia in that side stream, yeah, it's not uncommon to see, 1,000, 2,000 parts of ammonia leaving a digester, leaving the recuperative thickening unit. At the end of the day, recuperative thickening, it can continue to remove any proteins or any nitrogen caught up in protein form, but, any dissolved inorganic ammonia that typically goes right through the process. So absolutely, we have our own digestate treatment processes. not to get too far off script, but we also do a lot of nitrogen shortcut after these recuperative thickening processes. We'll basically drive the ammonia to nitrite, stop it at nitrite, and denitrify from there. So we skip the nitrate step altogether. Just kind of a quick shortcut removal process, but before it goes to like a mainstream wastewater plant. Pascal says we are working on a project on wastewater to energy with carbonate fuel cells. Do you guys do retrofits to ensure maximum gas recovery and subsequent supply to the fuel cells? That probably needs to be a side conversation. I really need to digest that, no pun intended. I say it's not my core area of expertise, so I'd have to kind of pick our process guys' brains a bit about that. I did look into fuel cells many, many years ago. As kind of a portfolio expansion. But we found that it worked very, very well for small applications. But based on our analysis at the time, it didn't really fit our portfolio for the size of applications we were going after. Shakti says, does recuperative thickening have any impact on inhibition on side stream deammonification? Process like THP to cause inhibition. So curious about the retention time, or curious about recuperative thickening, I think. Side stream inhibition for deammonification. That's a good one. That's a really interesting question because, deammonification, anammox, all those that kind of fit in that category. Those processes are, I'd say they can be a bit finicky when you get them working well and you have your organic load to, AOB populations within the right range, and you're able to suppress. So the difference between the AOBs and the NOBs. I had to put some thought into that one. That's a good question. I would be worried that there's still enough like residual COD left that it's going to create some issues kind of limiting how your ammonia organisms we can talk about that separately. Just out of curiosity, from Roberto, just out of curiosity, have you ever verified the SVI of the anaerobic sludges? Yeah, we have a lot of data on different operations. I mean, not to get too far sidetracked, but we still have the classical digesters, the CSTRs. We have the recuperative thickening units as well. It's kind of all over the map. Every industry is a little different. Some industries will have the whey factored into the equation. Other sites, it doesn't make sense to add the whey to the rest of the process. So all that kind of impacts the balance at the end of the day, and whether or not, we have a downstream biological system after that for further clarification or further biological treatment. Let's see, and Top Bit says, do you have any Fluence digesters operating in Iowa? I wish. I went to Iowa a few years ago for the anaerobic digester farm conference. It was really cool. The university put that on. Nothing yet. Most of what I've seen in Iowa has been ag based. There's a few big meat processors in the area that have lagoons that are being utilized, and particularly when you get down to the southern side of Iowa and get into Missouri, there's some big lagoon processes down there. Let's see. I think that's all the questions. Did I miss anything else, guys? All right. Well, I'll hang tight for another minute, but if no other questions, I think that about wraps everything up. I really appreciate it, guys. Oh, Roberta has a good question. Have you ever tested biofilm-based processes? Not to get into too much detail, the first, 12, 15 years of my career were based around biofilm systems. Did a lot of research and development, developed my own biofilm carriers through 2 different companies. Had a lot of fun with it, built, maybe 200 different biofilm facilities all over the world. In an anaerobic process, no, it's something that we have looked at And again, going back to former careers, it's something I was a part of in R&D, and controlling anaerobic biofilm growth on the biofilm carriers, particularly like the mobile carriers, the moving bed biofilm reactor style, is quite difficult. It's really easy for those things to get gunked up or for scaling to occur, precipitation to occur. I saw a lot of moving bed systems end up with so much precipitant over time that they actually sank to the bottom of the floor and bottom of the reactor, and there's not much you could do to get them resuspended. The other concern I always had with putting them into anoxic and anaerobic systems is just the mixing energy. A lot of times you're using mechanical mixers, and that can be a recipe for disaster if you're not careful. But can it be done? Yeah, I think there's probably a market for it out there. I know one or two companies that they're going to market with it right now. I don't think it's something that we'll go after. We have some other thoughts on ways to make the digesters more effective. All right. Well, I'll hang out for another 60 seconds, and
Thanks so much,
otherwise,
Jason.
yeah, thanks, Jessica.